Applications of differential thermal analysis. The applications of differential thermal analysis are as follows. First, applications towards inorganic compounds. Initially, the applications of differential thermal analysis were concerned with minerals and solids, but subsequently they were applied to pure inorganic compounds. DTA technique has been applied to the identification of mixed clays, lubricating greases, determination of thermal stabilities of inorganic compounds such as metal nitrates, perchlorates, acetates and oxalates, oxides of uranium and plutonium. Identification of new compounds in a specific reaction, purity of mixtures, investigation of solid phase reactions, kinetics, and polymerization have also been studied by differential thermal analysis. A lot of information has also been obtained from the differential thermal analysis thermograms of explosives and propellants. E.S. Freeman and V.D. Hogan investigated the thermal behavior of several inorganic fluorides and silicofluorides in air at 1 atmosphere pressure over a temperature ranging from 25 degrees centigrade to 800 degrees centigrade. Analysis of hydroxides. W. Lodding and L. Hamel developed a method to investigate the reactions and phase changes during thermal analysis of metal hydroxides. Differential thermal analysis is a very sensitive tool for the detection and measurement of gibbsite, that is aluminum hydroxide. Analysis is hampered by the presence of hydrated iron oxides, geothite, and lepidocrosite, which dehydrate at approximately the same temperature as gibbsite. In a strongly reducing atmosphere, differential thermal analysis method has been developed to determine the amount of gibbsite from the dehydration peak, regardless of the iron hydroxide present, by heating to a temperature of 450 degrees centigrade in a hydrogen atmosphere and then in air up to a temperature of 1000 degrees centigrade. The next application is towards semi-micro determinations. Charles Messiers designed a differential thermal analysis apparatus which permits micro and semi-micro determinations of materials weighing from 1 to 200 microgram or from 0.1 to 10 milligrams in controlled atmosphere between minus 180 degrees centigrade to plus 200 degrees centigrade. Thermal effects can also be detected. An example of this technique has been in the study of small lumps of metallic lithium within a crystal of lithium fluoride when it is subjected to thermal neutron irradiation. The technique has confirmed the findings that the crystal form of the precipitated metal is the face-centered cubic, which could be transformed into the body-centered cubic by heating. Another application of differential thermal analysis is towards zone melting. Zone melting involves physical separation based on the segregation of impurities during freezing. M. J. Yonek and D. R. Bailey investigated the system phenanthrene and anthracene by zone melting and differential thermal analysis and determined the phase diagram of this two-component system. The purity of phenanthrene and anthracene was determined by differential thermal analysis. Mixtures of purified phenanthrene and anthracene were prepared having different compositions and each sample was subjected to differential thermal analysis. In all cases, The endothermic changes in the organic system resulted in an increase in temperature difference between the sample and the block. From the results of the differential thermal analysis and zone melting experiments, phase diagram was constructed. Differential thermal analysis investigations help in identification, purity determination, and quantitative analysis of organic compounds, including evaluation of kinetic parameters of oils, fats, and pharmaceuticals. Determination of specific heat and heat of fusion. Differential thermal analysis studies permit the determination of heat and heat of fusion and specific heat on a variety of inorganic and organic compounds from a single calibration of an easily handled material, for example, like tin. Determination of isothermal crystallization rates of high polymers. J. Heiss developed a method for measuring isothermal crystallization rates of high polymers by following the heat generated during the crystallization in a double decker cell. The sample can be conditioned to destroy its thermal property prior to crystallization rate measurements. The method features small sample size, rapid measurement, conditioning of the sample in situ, variable atmosphere, and general applicability to most polymers. The sample is first conditioned in top block at a predetermined temperature for a certain length of time and is then pulled down into the bottom block capped at the crystallization temperature. The temperature differential between the sample and the inert reference material is scanned and plotted as a function of time by XY recorder. Differential thermal analysis technique is also used for the quality control of cement, textiles, glass, soil, explosives, and resins.